recording. So the difference between a balanced binary tree and a normal binary search tree is that in the end, the complexity of the search operation for a balanced binary tree is around logarithm base 2 out of n, where n is the number of elements. And this is very good because you have here a structure which is very performant on search. Just imagine you have n equal with 1 billion. If you try to do logarithm base 2 out of n, out of 1 billion, the degree is, it's a decimal value, I don't know, around 30 or 20 something. So this is, even if you have 1 billion values, the maximum number of comparisons that you need to do in order to find the searched item or to conclude that there is no item with that key in that tree is, let's say, around 30 or at most 30 comparisons, which is, if you compare the two values, 30 versus 1 billion, it's a huge improvement. So that's why the balanced binary trees are actually used for most of the databases index. Okay, so in MySQL, Postgres, Oracle, SQL Server, every time you define a key, a primary key for a table, then the database engine will build an index, and that will be a tree, or either a balanced binary tree or a B tree, which is a balanced tree with order n or m. So it can store more than one key, but they will always use these kind of structures because they are very fast on search. Okay, and like I said, the collection can grow to a huge number of values, but logarithm base 2 out of that value, it's will remain small. Okay, and that, let's say, will help you find the values very fast. Okay, now last week we talked about binary search tree, and we covered insertion, searching, printing. Okay, and the only operation that we didn't cover was delete. We just discussed it in terms of let's say in terms of theory. Okay, so we just exemplify it. And I told you that normally we don't use a binary search tree to store the values. We use it to store the index of the value. And the values are generally stored in a file because the hard drive is cheap and it can have sizes that can cope with any number of values. Okay, you can store 1 million students in a 1 terabyte hard drive. Okay, but you don't have 1 terabyte of RAM, and in order to reach that level, the cost, it's too much. So generally we store minimum information in RAM. Okay, and the data itself is stored in files. Okay, because the hard drive, the size of the hard drive is much more bigger if you compare with RAM, and the cost to expand the storage is very cheap, once again, compared to increasing the RAM size of your machine. Okay, so they are still different in terms of costs. Okay, so this week you discussed about AVL, which is a classic, let's say, balanced binary tree. Okay, and maybe you heard about others like red and black. It's another typology. Now, the only difference between them is how they are rebalancing themselves after each insert or delete. So here you have different algorithms, and AVL is one of them, red and black is one, and there are also other types of balanced binary search trees. Okay, so this was the topic for this week. Now, next week, you will discuss about graphs. Okay, and I think that will be the final topic. And I don't know if you covered, I will ask Mihai when you will cover B trees. Okay, so there are trees with more than one key in each node. Okay, so this will be the topics that remain to be covered. We discussed last week about the fact that a binary search trees used as an index in most cases. And I told you that the data, the records are stored in a file, and the index will keep the key and the offset inside that binary, inside that file. So because we have an extra seminar, and after, when we finish today's seminar, I will check the doodle to see what are your options, and after that I will show you the final decision. Okay, and we have an extra seminar, so we have an extra time. Now let's do today something which is very close to a real scenario. So we will cover the a binary search tree, but used as an index. And in parallel, the data will be stored in a binary file with direct access. Now, I don't remember at which point we cover binary files. Okay, I think in seminar 3, I found here some. Yeah, okay, so you have file name, username, password, okay, struct db, create db, and here we insert them. And I think it was a direct access file, okay, if that was the case, or it was a binary sequential file. Let's see, I'm checking, let me show you. So this is the source file from seminar 3. So here we had an address, static field, so fixed size. Here we have a package. Now this is a fixed size. Here the contact is dynamic. And what I want to see is how we have written the contact, okay, inside the database. String cut create db, no, connect, right. So yeah, so we have written the structure as a fixed size package, because we converted here the contact to a 1000 buffer. So even if in memory the contact was a dynamic field, here we are storing it as a fixed buffer of 1000 chars. Okay, so this is very close with a direct access binary file. Okay, so let's do this example, and we covered today also delete, because I will not insist on how do we do insert. We already explained that last week. Okay, so we will just focus on the example. Okay, and we cover delete, and also we see a real, let's say something very close to a real life scenario where we use the binary search tree as an index. And like I said, an index is storing the key and the offset inside that file. And when we do the extra seminar, I will cover the AVL part. Okay, and I will record the seminar as the others. So I will try to upload them this week to have all the seminars at your disposal, because we dive into the last 2 weeks phase when everybody's starting preparing for the exams. So you need the recordings. Okay, so we will do the AVL, or we just start the AVL discussion, because there, even in a seminar, I don't think we have enough time to cover all rotations that will help us rebalance the tree. And after that, we have 2 extra weeks. Okay, so next week we will continue AVL or start graphs. And in the last week, maybe we'll do a recap, or if the course is not advancing on B trees, maybe we choose our own subject, because the test is on Wednesday. So on Tuesday, we have our regular seminar. Okay, so we don't lose any seminar. Okay, so let's do this example. So the idea is, this is very similar with the real database. And now if you implement an interpreter, something that can allow me to write select, update, delete, now you can create your own SQLite database, okay? Because this is an SQLite, okay? It's a very simple program which is managing some files, and for those files, when you load the SQLite database, it's also loading the index structure into memory. Okay, so standard input output. Okay, and we need also malloc. Okay, and I think string.h. Okay, so what we want to store in the file, and once again, I will choose dynamic fields because I want to remember to help you remember that in a direct access file, which is a binary file, is not a text file, all the records should have the same size. Because if you know this, then it's very simple for you to determine what's the loop size. How many bytes do you need to jump from the beginning of the file in order to reach a specific record? Okay, so this is mandatory when you hear direct access file. If it's a sequential file, it means you don't know where the record is, so you need to read each record in order to find that one. So it's not efficient because you will do a lot of reads from a file on the hard drive, and this is one of the slowest operation that you can do on a computer. Okay, so try to reduce as much number of reads and writes from a file because that will slow you down a lot. Okay, so let's define here a basic data structure. Okay, we can do student. Okay, and I will choose dynamic fields. Okay, so I will have a name for the student. I will have char faculty. Okay, and maybe an array of grades. Okay, number of grades. Okay, so this will be our structure that we can use in order to store our data. And remember, if we talk about an index, you should always look for that unique value which you can associate with the article. So you need a key. Okay, so here we need the ID. And this should be unique for each article, because if this is something you don't have, you can't use a binary search tree. Okay, you can't use any structure which has been defined for searching. Okay, because the entire logic of searching is, in this case, to search for unique keys associated with the value itself. So you search by its key, and after that you get the value. Okay, so we need this unique value here, because otherwise we can't search for a student. Okay, so this is the student. Now, because we will write this in a file, in a binary access file, and you see here, if you take two students, one is Bob, one is Alice, one is at cybernetics, one is, I don't know, at physics or mathematics, and maybe Bob has 5 grades and Alice has 10 grades. If you compute the size of each student, is completely different. So if you want to store that in a file which can give you direct access, a prerequisite for that is that each record in that file should have the same size. So at some point we need to convert our student to a fixed size student. So this is transparent for the user, and this is like a static size buffer. So each time we take real students, we convert them to that static buffer, we write the buffer. So this operation, we can do this operation in both directions. Okay, convert from a static student to a normal student and vice versa. So let's define that structure. So this is needed for the direct access file, binary file. Okay, now you can skip this part and do this translation in your functions, read and write functions, but you need to take care in order not to do mistakes. And remember, I always recommend you to approach complex problems. For example, a function which is doing more than one thing, try to split that multiple tasks in other functions. So in this way, it's very easy to manage complex stuff, because each time you focus on only one piece. So your mind will focus only on that action. And after that, you reuse that action. And if it's implemented correctly, every time you use it, you don't have any issues with that, okay? So let's try to do this intermediary structure. So this is something that will help me manage more easily the solution, okay? So struct fixed size student, okay, fixed size student. So what do we have here? We have the ID, and for any dynamic field that the real structure has, like name, faculty, grade, so here I choose all the fields to be dynamic, just to exemplify that, I will define a static correspondent. And here the only problem is to choose a size which should be bigger enough to cope with any real values. So for the name, okay, I can choose, let's say 1000 charts. I think that will be sufficient. Now, when you do this kind of stuff, when you hardcode values, you also can, I don't know, maybe later you decide to change them and some parts of your source code will remain with the previous value. So it will be a mess in the end. Try to use variables. So for example, here I can define before all my structures, I can define some variables that let's say are very important to me. So int, let's say a name size. Okay, so I define them with caps just to emphasize the fact that they're important. So 1000 charts. Now, what else do we have? I think the faculty can be stored on the same size, but let's say faculty, but you can use name size. And in that case, you name it differently. It's like string size or char array size. Okay, now for faculty, let's say 500 chars. And for grades, max grades number. Okay, let's choose for the maximum grades number. We do an analysis and there is no way that any student will have more than 50 grades. Okay, we can check all systems, whatever. You can increase that to 100, but I think 100, it's already a lot. Okay, so max grades number 50. Now, if you try to use these sizes as values here when you define a static array, so if you want to use name size, okay, now here you'll get the compiler error, and the compiler is like, you know, this field is created when you compile this. So if you pass me a variable that can change its size, this is a very dangerous thing to do. Why? Because I will create your name array here with 1000 chars, but later you can easily change this size to any other size, like 5000. So this is a dangerous thing for you as a programmer, because later if you change that variable and you want to go through that array, you will get easily into index out of bounds. Okay, so in this case, the Microsoft compiler is trying to alert you that this is not safe because this variable may change in time, and here in your mind you will say, hey, this array has this size, but the size later can change, and that can lead you to very strange runtime exception. Index out of bounds could be one of them. So here the Microsoft compiler is trying to either make you use a hard-coded value, which will never change in time, or to make you, exactly, to define this as const. So in this way, the Microsoft compiler knows for sure that if you try later to change the size, you can't. And I always tell you that there is a big difference between compilers, and some compiler errors that you get here in Visual Studio, they don't exist on other compilers. Okay, and this is one case. For example, on Linux, this is not an error. So on Linux, you can use name size here for GCC, the GNU C compiler. There is no issue with that. Okay, so once again, it's very important to know your compiler, okay, because some compiler errors are related with a specific compiler. Now, in this case, I think it's a good thing you get that error. So const, okay? And generally, if you define global variables and you define them not to use them, you know, we are not allowed to use global variables, but if you define them as fixed values, that's okay, okay? So try not to use global variables as normal variables, but if they are constant, which means they are like beacons with specific values, that's okay. So char name size, char faculty size, grades, and here I have grades, and here I have maximum number of grades number, and number of grades, because I don't know how many of this maximum grades number I'm really using. Maybe I have only 10 grades, so I'm using only the first 10 integers in this. Okay, so we have this structure, which is something intermediary, is needed only by us in order to manage the direct access binary file. Okay, so let's go for some functions to initialize this structure, for example. So here I'm returning a student, init student. Okay, so let's go for all the values. I need the ID, the name, I need the faculty, and its grades. And this is an array, and int number of grades. Okay, so let's initialize it. Student. Okay, and now let's initialize student ID equals ID. For name faculty, we need to create space. So student dot name equals char asterisk malloc of size of, or strlen of name plus 1. Okay.
You forgot an equal sign.
Yeah. I was searching for that thing. Okay. Thank you. So this is the name. Don't forget to copy them. So it's a two-step process. Student name and name. Now let's move to the faculty. Faculty equals char asterisk malloc string length of faculty plus 1. Okay, and string copy student dot faculty. Okay, so now we copy the values, and now for the grades we did that in previous seminars. So after we initialize the student dot grades equals int asterisk malloc, and here I have size of int multiply with number of grades. Okay, and the semicolon is here. So after we do this, we can copy the values one by one using a for, or we can use a mem copy. Okay, so the destination is student grades. If you don't like this part, you can use for int 0 blah blah blah. Okay, and the source is grades, and the size is number of grades multiplied with size of integer. Okay, so now we copied the array, and let's not forget copy the number of grades. Okay, so now we have the possibility to init a student. Okay, let's finish the student part and let's return it. Return student. Okay, so this is the initialization of a student, and in order to finish with the student, we need also void print student to test our data. And here I'm receiving a student. Okay, so I have printf %s dash %s. So here I pass the student name and the student faculty. Okay, and after that we print the grades. So let's check if we have some grades. So if student, but if we if the number of grades is 0, the for will not execute. So here will be \n, and also add on a \n here. So grades, and here I'll have for int I at 0, I less than student dot number of grades, I plus plus, and let's print them. Printf with an extra space here at the beginning, %d, and here I have student grades at index I. Okay, so now we can initialize and print a student, and this will be useful in order to test our solution. Okay, now what do we need here? We need a function to convert a student to a fixed size student. Okay, so in order to do that, fixed size student, we write a function that give us a fixed size student, and here we have convert to, let's say, to fixed size. Okay, so here we need a student, a normal one, and we need to convert that student. Okay, so what it means, we create a fixed size student, and because a fixed size student has static fields, it's very simple to convert them because we don't need to create any additional space. So it's all about string copy, fixed size student dot name, and we take the name of a student, name. We do the same stuff with the faculty, fixed size student faculty, and we have a student dot faculty. Okay, don't forget about the ID. So here we have a fixed size student dot ID equals student ID. Okay, and for grades, fixed size student dot grades, sorry, number of grades equals student number of grades. Now we used the mem copy earlier. Let's copy them with the classic loop. I less than student dot number of grades, I plus plus, and now we copy them. So fixed size student dot grades at index I equals with student dot grades at index I. Okay, so this is the conversion from a normal student to a fixed size student. So we know that at this point, all the students, if they are converted to a fixed size student, they have a fixed size, and it's easy to compute that size because all the arrays are static ones. So return the fixed size student. Okay, and the reverse conversion, because we will need this in order to read back the students from the file. So you extract it based on the index from the file, and after that, if you want to use them as students, because that's your official structure, you need a reverse conversion. So here, this is the opposite function. Student, convert to student, fixed size student. Fixed student. Okay, let's read this name of the variable. And here it's simple because I can use student equals init student. I can use the previous method. So here I will pass fixed student dot ID. I can pass fixed student dot name, and after that the faculty, fixed student dot faculty, and the last fields are fixed student grades and number of grades. Okay, so you see how reusing and writing small functions becomes productive, because now each time you need to do something, you reuse that function. So you focus here on only the new part, what's convert to student is doing in addition of creating a student. Okay, so it takes a fixed student and you just return that. So return student. Okay, so at this point we know how to create our main data, because this is the data that we need to process, a student, and everything else are actually tools that will help us manage students in a very efficient way. So the B tree, the binary search tree, it's a tool, it's an instrument. The file, it's an instrument. Okay, so this is the data. Everything else, it's an instrument. Okay, so we know how to do these conversions. We know how to print them. So let's define the structure for a binary search tree. And this is actually the structure of a balanced binary search tree. So the only difference is what is happening when you insert and delete, and that's it. But the structures are the same. So let's define that structure. So let's say this is the student index node. Okay. And here, like I said, you need a unique value. So we have that unique value is the ID of a student. And now we have the offset. So here I'm using a long integer, long. I can even use a long, and I think this is a 10-byte integer. So it can cover very huge files. Okay, so we will not have problems there. Offset. Okay, so for each student, we know where its location in the binary, in that binary, direct binary file. Okay, so student index on ID long offset, and we need the two pointers, which is student index node, let's say right, and student index node left. Okay, so this is it, and don't forget to initialize them. Okay, now let's write the function that will init the student index node. So here, for any dynamic data structure, always return a pointer to that, never an article. So student index node init node. Okay, so what do we need here? We need the student, and that's it, student. So student index node new node equals student index node asterisk malloc, and we need to create something with the size of student index node. And for that part, we need only the ID, because we still don't have the offset. So this is a virtual node. We don't have the offset. So new node ID equals student ID, and try not to forget to init your data. So for example, this should be 0 by default, but let's be sure that it will always be 0. So offset is 0, which means we know it's at the beginning. Or you can set -1, and in that way you can validate it, because 0 at this point could be the first student in the file. Okay, is the first one.
What does this variable hold?
Sorry?
What does the offset hold? Like, what does it represent?
So this is how the final solution will look like. So let me open the whiteboard just to make it clear why we need it. Okay, yeah, got it. So let's suppose we need to store several students, and the primary key is their ID. So in the end, I can easily search for those students by their ID, okay, because it's unique. So in the end, we will have what? We will have this file here. So this is the file, okay, and where is the, I need to close this one. Okay, text. So how do I, oh, whatever. It's still an issue for me how to use the whiteboard. Okay, so this is the students dot, I don't know, bin, binary file. Okay, so here you will have all your students, and we will use to store students the fixed size. So each student will have always the same size, okay? So this will be the first student, let's say X bytes, okay? So we can compute, I think it's several hundred bytes. So this is student 1. And after that, you have student 2, okay? The same size, X bytes. And after that, you have 3, okay? And at this point, maybe we have 50, the student with ID 50. And after that, you have the student with ID 1001, okay? And here, because maybe this is the order that we insert them in the database, here you have the student with ID 7. Okay, so you see, they're all relative with the beginning of the file, okay? And when you open a binary file or a text file, you will always are here at the beginning. And this is offset 0, okay, relative with the beginning of the file. And after that, we will create this binary search tree. So here you'll have ID 1. And after that, we receive 2. So 2 goes here, okay. And after that, we receive 3. This is the problem, you see, with the binary search trees. If you get the values, the keys, if you get them sorted, your tree will grow on a diagonal, and this is like having a list. This is the problem with the binary search tree. It's vulnerable to series of values which are already sorted, because you will lose the property of the trees. Like the size of the tree is equal with n. So this is a list. Why to bother with right left when you can do it with only one pointer next? Okay, if your tree will grow like this. So that's why you need balanced binary trees to rebalance the tree, to move part of the values to the other side. Okay, so you get 3, now you get 50, okay, and after that you get 1001. So yeah, it's perfect, this example, to show you what's the problem with the binary search trees. And now you get 7. Finally, we get something different. So 7 will go here. Now, it's very fast to search here, okay? For the student base, it's on ID. So we see 7 or we see 50 here. Now, when you find it here, how can we reach to 50, to this student with ID 50 instantly? So using the search in this binary tree, we reach this spot. How can we reach instantly this spot here, okay, where this student starts? Now, if all the students in this file have the same size, it means in order to determine what's this offset, okay, because we have a function called fseek. So starting from this point, we can reach this location instantly. Okay, in order to find it, we need to compute the offset, okay, of that value. So this is the offset. So the offset is a relative distance to something, to a fixed point. It's like Einstein said, okay, give me a fixed point in space and I can move everything. So if you have a fixed point in space, you can compute the offset of everything else relative to that fixed point. Okay, this is the offset. So if I know the offset and I'm here, I can easily jump here using fseek. Okay, so this is the scope of the index. The data is here because we have space on the hard drive. We use this binary search tree to search for keys. And if we find the key, I will have its offset. So I will open the file and get the value here, the entire student. Okay, so that's the scope of that offset, is the relative distance from the beginning of the file. Okay, so that's why we need it. And I was saying maybe sometimes I think maybe it's better to set the offset -1 in order to say, hey, this node points to nowhere, because 0 may be considered, yeah, let's go for -1. 0 may be considered to be the first one. So an offset 0 is actually where your file starts. So it's a valid offset. It's the beginning of it. Okay, so this is the init node function, and we need to return it.
So what does it mean if the offset is -1?
So this is like, if you check that and is -1, maybe it will mean to us that maybe the record is not in the file, or I don't know, maybe the new node has not been initialized completely. Because in the binary search tree here, all our nodes should have two informations, the key and the offset. So maybe when we create an init a node here, because when you insert something here, okay, in the binary search trees, maybe you don't have the offset. Maybe you didn't insert the student already here, so you don't have the offset. So let's say this is one way that we can check if that student, if this student is already in the file or not. Okay. So yeah, it's like when you have a char asterisk and you want to print it, you always check if it's null, because sometimes, I don't know, you may reach a scenario where you forget to initialize that pointer. Okay, so let's say in this case, it means the student is not stored in the file. Okay, because like I said, 0, it's a valid offset. So that's why I'm not using 0. Okay, now, obviously at some point, we need to initialize the offset. So let's create a function for that. Void set offset, set node offset. So in this case, you need what? You need a student index node. And because we always process them by their pointer, we already got the pointer of that node. So we receive it by its pointer, so we can easily change it. Okay, long offset. Okay, so here I will just initialize it. So we receive it by its pointer, so we can do that easily. So node offset equals offset, and that's it. So this is set node offset. Okay, so we know how to create a node. We know how to change its offset. Now, what else do we need in order to start writing insert, search, and managing the file itself? So in order to manage the file, because managing a file means managing a pointer, so we did that. Let's define a structure. Let's say binary file. Okay, so here I need a name for that file. Let's go for something. I will avoid dynamic fields just to simplify this part, because we already covered the dynamic parts. Okay, and here I need the file structure pointer, pf. Okay, now let's write some functions for opening the file and closing the file. So void open file. Now, when you open a file, let's open it, and in that case, binary file. We return a binary file structure. So here I need the const char asterisk name of the file. So what I will do, create a binary file object, file, copy the name into file name, and this is file name. Okay, and open the file. So pf equals fopen. So generally, because we work with binary files and is returning a binary file, so the file name is file.name. And the opening mode is, let's say, read binary plus, which means read write. Okay. And it's binary because by default they are considered to be texts. And pf is the file pf attribute. Return file. Okay, and in order to close the file, let's write a function for that, close file. Now we will receive a binary file, and when you close the file, in order to be able later to validate if we have an open file or a closed one, we will set the pointer to null. So each time we close the file, we set the pointer file to null. So in that way, we can easily check if a file is open or not. Okay, so in order to change a value inside the structure, always ask yourself, hey, this function is changing any of these two attributes, name or pointer. And in this case, like I said, we set pf to null. So if the answer is yes, once again, pass it by address. So fclose file pf and file pf equals null. Okay. Now, if you want to check, and this is like is open, the equivalent function from file streams in C++, if you want to check if the file is open or not, is open. We can write a very simple function for that, is open. And here I will receive a binary file. I don't want to change anything. I just want to check something here. So here I can do using the condition operator instead of writing an if then else. So here I can do return. So what's the question? Is file.pf equals to null? So if it's null, this is the question. We return false because it's not opened. And if it's different than null, we return true. Okay, so in this case, we have a very short function that you can use to check if the binary file is open. Okay, so at this point, we know how to read and write something in the binary file. Okay, now, and because it's a direct access binary file, let's cover the read and write functions. Okay, so if you give me the file and the offset, I can easily read and write anything there. Okay, so for me, this is very straightforward. So
I'm sorry.
Yeah.
Why do we have one binary file, pointer file, and one normal one?
Here and here.
Yes.
So you have two functions, right? They
Yes.
both receive a binary file article. Okay.
Yes.
So anytime you pass something to a function, you pass it by value. You give the value of that variable. So in this case, you have two functions, each receiving a file article. What's a file article? It's a structure that has a 50-char array, which is called name, and the pointer. So the size of a binary file variable is 54 bytes. Okay, we know that. So you have two functions which receive that article, that variable of 54 bytes. And this is the way you write the function, and this is the way you pass the value to that function. And now this is the $1 million question. Is that function, and you ask this question for each function at a time, is this function going to change something in that space of 54 bytes? So what's the scope of this function? To close the file. So what it means for us? It means call fclose. Is fclose changing any of these two variables? No. Fclose is actually instructing the operating system to close the cursor on that file on the hard drive. So by calling fclose, none of these two variables are changed. Okay, so at this point, the answer is no. The file, this function is not affecting the article. Now, how do you know if I'm giving you a PF pointer? How do you know if the file is still opened or closed? You don't know. What you can do is to try to open it again, and maybe you have a runtime exception. But if I'm giving you a pointer to a file, you don't know in C. In C++, it's a different philosophy because it's an object there. But here, you don't know if the file is still open or closed, because fclose is not changing the pointer value. It's just closing the file and that's it. You remain with the PF pointer that has a value, but no one announced that pointer that the file is not more opened. Okay, so in order for us to be sure or to test in the future that after we close the file, we need to reopen it again because it's closed, we do this thing here. And this is our, let's say, our role. We set the pointer to null. So let's ask the question again. This function, close the file, is changing the values of any of these two variables? The answer is now yes. You see, I'm changing the pointer value. So because I want to make this change be still available after this function has terminated, because here we are working on a clone of a real file, which we will define in main, and we want to persist the change. That's why if the answer is yes for at least one attribute, you need to pass your variables by pointers in C, or if we were in C++, you need to pass them by a reference. Okay. Now, if I switch to isOpen and ask the same question, is open going to change any of the two variables? No. So in this case, why to bother? You can still use a pointer. Okay. You don't change anything, but let's say we don't want to bother with the pointer if we don't need it. Okay. So that's why you have the one is by pointer, one is not. Okay.
Yeah.
Okay. So let's implement the two other methods, which are used for writing and reading a fixed size student from a binary direct access file. So let's start with the write one. So void write student into file. Okay, so what do we need in order to write a student into a file? We need a binary file. Okay, and we need a student. Okay, so how this goes. So we know that a student has a variable size length because the name, it's a dynamic field, faculty, it's a dynamic field, grades. So that's why we have our intermediary, let's say, type, which is a fixed size student. So for the first thing that I will do is to convert my student to a fixed size student. Fixed size student, fixed student equals convert to fixed size student. Okay, so now I have the fixed size student because this is actually the value that I will write into the binary file. So how do we write a fixed student? So if the student has only static fields, you have all the values in the article. This is the problem with binary files. If you have at least one dynamic field, don't write the student entirely because you will write the address of that pointer. So that's why you need to convert the students to a fixed size students, meaning we need to have a version where our data is stored here inside the student itself. Here is not inside the student because the student has a pointer and the name and the faculty and the grades are elsewhere in heap. The student itself has only the addresses of those values. So never write in binary files addresses, always write values. So that's why we need to remove all our dynamic fields to something which is static. So I know for sure that all the values are here in the fixed size student. Okay, so having this conversion, we solve this issue. Now, I can write the file. So let's open the file. Okay, so file, let's check if it's opened. If file, sorry, if is open file, so we already know it's opened. Okay, now or let's be pessimistic, because in the end we reach the same spot. We will write the student. So if it's not open, let's open it. Open file and pass the sorry, it's yeah, open file. Yeah, but here I get the name of it. Okay, so binary file, or file, let's say file equals open file of file.name. Okay, so now the file article is recreated and we get the new version here. So we get a new version, but what I'm actually interested in is the pointer. So now I know for sure that the pointer is not null, but always check this, okay, just to be sure. So and also we had this rule that each time we do some changes, we return 1 means it's success, 0, let's say, or -1, it's a failure. So if we are not able to open the file, maybe you don't have rights on that hard drive. Maybe, I don't know, something has happened. The operating system is not giving you the file, so you don't get it. So once again, let's, after you open it, okay, so we open the file here, but let's suppose we get it. Open file. Okay, so let's see. What I wanted to write is this, but I think it's redundant. So if file.pf equals with null, return 0, which means we don't have access to the file. So we can write this. So we don't have access to that file. So here we try to open it, but we don't have access to it. Okay, so PF is still null. Okay, now if you receive a file and this returns true, we don't need to open it, so it's already opened. Okay, so we don't have access to that file, and I think here it's better to work with the file name and not play with the binary files, because that can be an issue. Yeah, let's change this. Const char asterisk file name. And I think this we cover all possible situations. So we always play with the files by their name. Okay, so binary file equals open file of name, file name, sorry. So here we try to open it. If we can't, we don't have access to it, it means someone is preventing us to open the file, we return 0. So we know that if you get 0 here, it means we didn't had any chance because it didn't allow us to open the file. Okay, so this is the file name.
What happens if there's a file with the same file name already?
Yeah, this was actually the thing that I was trying to see. So when you open the file now, read binary plus is by default truncate. So by default, we'll do what? Override the existing file and we lose the database, right? So here we need to do append always in append mode. So what was the combination for append? Is read binary, I don't know, it's an A there. Let's see, C, open file in append mode. Okay, let's see. Yeah, it's append. So yeah, and for C, open binary file. So you need an A. Okay, and blah, blah, blah. Read binary A plus B on your need. Okay, blah, 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 A plus B, A plus B. If you use A plus B, okay? Okay, so let's open it in A plus B. So let's say this is append mode and binary. Okay, so we go for A plus B. Okay, append mode. Now, what's the problem with append mode is that the file cursor for read and write are always at the end. So you need to take care of this. You are always at the end of the file. So here you may have two different functions, open a file for appending or open file for reading. But let's keep this file. So this will always place ourselves at the end of the file. Okay, so if we are here, which means we have the file, we are at the end of it, what do we want to do? To write the student into the file perfectly. So how can we write that? We can write it instantly. Okay, so fwrite. What do we want to write? The fixed student. And remember the questions. So always start with the variable that you want to write, fixed student. Now, is this the value or its address? It's the value. So how do you get its address? Ampersand. Okay. And after that, how many you have element size, element count. What's the size of this element? Because it contains only static arrays, I can easily compute its size by using size of fixed size student. So this works for articles that they don't have pointers in them. Okay. And how many elements? One. Where do you want to write that? Into file pf. Now, this will write the student. What do we need when we write a student into a file? What's the information then we need it back in order to build our index?
The offset.
The offset. Okay. So fwrite, it's returning generally the number of bytes that he has succeeded in writing, but you don't get the offset. So how do we get the offset of this student? We need the current location into the file right before writing, not after writing, because after writing, you are after the student. And the offset, we need the offset of the beginning of the student, not its end. So here, let's get the current offset, which is our current location into the file, which means at the end. So long offset equals, and here you have ftel. Okay, and this will return, you see, a long, and here the file .pf. So now you get the offset. Now we write the offset here and let's return it. So we need to change this to a long. Okay, so because the first time we will write a student into a file, the first one, the offset will be 0. Let's change our codes. So -1 means we don't have access to that file. And here, if you return the offset, and the offset could be 0 and upper. Okay, so any value starting with 0 will be considered a valid offset. Okay, and -1 means we didn't have any chance to write that student because we couldn't open the file. So this is long write student into file. And that's it. So you just need to find the correct location and write that student there. How do you update a student, for example, into that binary file? So void update student from file. So here, once again, we need the file name. Now, if you always get the file name before, don't forget to close your files. Close file, because otherwise the next time you will try to open it, you will get into a runtime exception. It will not open it again. So you can have only one read and write access cursor on a file. So here I'm calling close file to close this file. And you see, because we just explained why we pass by address, here I need to pass the address of file, but here we are closing the file. So once again, const char file name. And now we need what? The student, new student value. Let's say this is new student value. And when we update a student into a file or from a file, you need what? Long offset. Okay, so you need the offset of the student inside that file. So what do? Once again, a fixed size student, fixed student equals convert to fixed size student, the new student value. Okay, we converted that. Once again, open the file. So I can get this one. And in this case, I need to return an integer or an error code. Okay. So we open the file and it's once again in append mode. So remember, we are at the end. So what do we need here? We need to place or change the location to the given offset. Okay, how do we do that? fseek, where into file.pf, what's the offset where we want to reach? Offset. Okay, and what's the origin? And remember, when we play with direct access binary files, all our offsets are relative with the beginning of the file. So this is seek. So this is current, this is the end of the file, and seek set means at the beginning, okay, which is 0. You can write 0 is the same. This is a macro. Okay, so now we are there at that location. Okay, now the only thing that here you need to validate if you have that offset. Maybe you are trying to update a student which doesn't exist in that file. Okay, you receive a wrong offset. So how do we do that? Once again, get the current offset. So you can copy this file here. And let's check them. So what's the validation rule? Let's say this is not the same variable. This is the current offset, which is actually the end of the file. So what's the validation rule? If the offset which is given here is bigger or equal than current offset, it means someone is asking us to update a student which is out of that file. Okay, is not part of the file. So in that case, return, let's say -2. So it means the received offset is not valid, is outside of the file. Okay, so this is something we need to validate. And if everything is okay, we are there. How do you update an existing student? You overwrite it. This is it. You don't try to see which attribute is different. Don't bother with that. Just overwrite it. So fwrite, what? The fixed student. Okay. What's the size of this article? It's size of fixed student. Okay. How many elements? 1. Where? Into file.pf. Okay. So now we overwrite it. And in this way, we update the existing student. Okay. Don't forget to close the file. Close file. File pf file, sorry. And once again, we need to pass it by address. and let's return a success, return 1. Okay, which means we update it. So you have -1, -2, or 1. Okay, so in this way, we update the file. So we know how to write, we know how to update it. Let's cover read. So when we read a student from a file, we return the student. Okay, so here we return a student, read student from file. Okay, once again, const char asterisk file name. And what do you need? You need the offset. Long offset. So the same drill. It's like almost copy pasting this entire part here. Okay. We need to make some changes because here you see we are returning -1. So let's try this because I think we need to change most of the instructions there. So this will be our result, student result. Let's say init student. And here the ID is, let's say -1, empty name, empty faculty, null for grades, and 0 grades. Now, I think we have a problem in init student because if you try to malloc, I don't know how that will behave. I know for sure new will throw an exception if you try to create 0, to allocate 0 bytes. So let's see what will happen. But I have here, I'm not sure about this. Okay, and I'm not sure about actually the init student function, how malloc will behave when we try to create 0 bytes. Okay, so this is something we didn't cover yet. Now let's finish read student from file. So init student, okay, and we need it. So let's open the file. Binary file equals open file of file name. Okay, if the file is not open, if not is open file, once again we have a problem. So return result, which will return a -1 ID student, and for us this means we have 0 results. If we open successfully the file, once again long current offset, once again ftel file.pf, and once again we need to check this offset. If offset is greater or equal than current offset, once again return result. There is no student there, it's out of the file, we don't have this offset. So if the file is opened successfully, if the offset is okay, is inside the file, now let's locate the student. So F6, yeah, what, someone tried to say something?
Yes, I asked what was ftel doing, like what
It's giving you the current location in the file. So you do reads and writes, and at some point you don't know where you are in the file. Okay. So ftel will return the current location in the file, and it will always return the offset of that current location. So offset is always relative to the beginning of the file. So you did some reads, you are in a 1 terabyte file, and at some point you don't know where we are. So if you call ftel, it will say to you, hey, you are at, I don't know, 10K kilobytes inside that file. Okay, so in this way you get the current location in a file. This is ftel. Okay, now we need to locate the student, so we need to position ourselves inside that file at the given offset. So fseek file.pf, and the offset is the one that we have received, and the origin is seek set or 0. Okay, so we are here. Now, how do we read the student? We know all our students have a fixed size, which is helpful because I can read it entirely. Okay, if you check seminar 3 or 4, when we did binary files, there we serialize them. So there we have written each student piece by piece because we had dynamic fields. But here, because I have the fixed size alternative, I play with that much more easily. So let's read the file, read the student into a fixed size student, fixed student. Okay, how do we read that? Fread, where do we read it? Here at this address, fixed student. How many bytes? Size of fixed size student. One element from file.pf. So remember, this always work only if you don't have dynamic fields in your article. If you have at least one, this is the biggest mistake that you can do, reading and writing the entire article. We discussed that in that seminar, but this is something you need to remember. Okay, so now we have the student. How do we convert it? We have a function for that. So result equals convert to student the fixed student, and that's it. We return it. Or you can just write return convert to student, return result. Okay, so now we know how to read, write, and update. An interesting story is how do you delete? Because if you are in a file, can you delete this piece here? So can you delete this? For example, can you delete it?
No.
No. If you want to delete it, you need to write a function that will, this is like inserting or removing an element from a dynamic array. It's the same story. So if you really want to delete this one here, okay, you need to create a new file, copy all the values from the beginning up to this point, jump this element, and copy the rest of them. So you need to create a temporary file, copy all the values without the one that you want to delete, and after that, delete the previous file and rename the second one. So it's quite a struggle here to do that. It's not so easy. So because remember, the hard drive, it may have 1 terabyte, 2 terabyte, 10 terabyte. So even if we need extra space, I don't know, we rent that into, so we rent virtual storage. So there it doesn't matter. The virtual storage will have, I don't know, 100 terabytes because they are using virtualization, multiple drives. Okay, so it's cheap. So deleting a student from a direct binary file, sometimes it's much more easier if you, I don't know, write here -1, for example, okay, just to mark that this student at this location, it's deleted, is not used anymore. So change its ID to -1, for example. This is a way of saying that this student here doesn't exist anymore, and just leave it there. Now, you may say at some point the file size will be big, but inside that file, you have a lot of unused locations. So at this moment, you can do a, I don't know, a management routine or a optimization routine, and you can optimize the files, but by actually removing all those unused records. Okay, and you do that only once. It's like with hash tables, you resize it only when you reach its maximum capacity. Okay, but without this, deleting a record, it's much more easier to do a logic delete rather than a physical delete. Okay, because it doesn't matter. Yeah, you have there 500 unused bytes. Who cares? We have 1 terabyte left, so we can do that for a lot of times. And okay, you gain performance because otherwise this is a very costly operation. It will slow you down if you do that after each delete. Okay, so this is something you can implement differently. Okay, so delete can do a logic delete, which means you set there a -1 for the ID and that's it. Okay, you just ignore that student. Okay, so that will be the delete part. Okay, so with this, we can create students, read and write the students from the file. We need only the binary search tree and that's it. So we will have a final solution. So let's go back here. We have already a student index node. Okay, so let's define a structure to handle the entire index, because I don't want to play with a pointer to a student index node. So let's define a structure for managing the entire index. So here I will say struct student, let's say table index. Okay, and here we know we have the root of the binary search tree. So I have a student index node root, and maybe here you have a char, let's say key name. Okay, 50 chars. So in this way, you know that you have this index for the student table, and the key name is called ID. So it's a primary key. Okay, now if you still want to, let's say, store the table, you can also have here table name. And for that table, we have a file associated with that. So in this way, this is called primary key. This is actually primary key. Okay, let's write a function that will init a primary key. So primary key create key. Okay, so what do we need? We need a const char asterisk column. Okay, you need a const char table, const char table name, and that's it. This is the only thing that you need. Here we just copy into, let's create the primary key, let's call it key, and here I will just copy into key dot key name the column name, and here I can do a string copy on key dot table name the table. Okay, so at this point we can initialize it, and here you have return key. Okay, and that's it. Don't forget to initialize the root. This is very important. Key root equals null. Okay, don't forget to manage that. Okay, so now we can create the key. So let's start initializing our key here. So let's say primary key ID key equals with init create key, create key. So the column name, it's called ID, and the table is called students, for example. And here we can use this to for the file name, okay, to create the association between a virtual table and the file name. Now, what do we need here? We need a function that will insert something in a binary search tree, and we covered that. So I will just write it. I will not explain it again. I will give you the recording from last week where we had the, let's say, the detailed discussion on that. So in order to insert something into a binary search tree, we need a function that will return. And remember, I asked you last week, how do you want to write insert? Do you want to pass the root pointer and change it, and so we will pass it by address, or we return each time the root node? So we choose the first version, and later we realized it was not our best decision, because the way insert has been written looked very, let's say, difficult to manage, because each time we pass the address of the next pointer or the address of the right pointer. And we all conclude last week that it was better next time when we write insert to return the root node each time. So we remove a pointer, okay? And the syntax is much more cleaner. So this time, let's avoid that decision. It was not a mistake. The code worked, but in terms of how easy it is to read and write that, I think it's more complex than this version. So even the last week solution was okay. Okay, it's just, let's say, a preference regarding how easy it is to read and write the same function. So in this case, I will return a node here each time. So student index node, okay, insert binary search tree. What do we need? We need the current node, root, and obviously we need the student. And because this is an index-based node, we need also the offset. Or let's do it differently. Let's ask here for, we have a structure that is storing that. Close file, open file, student index node. No, because this is here, the offset is there. Okay, so yeah, let's ask for the student, or let's ask for, because we need only the ID and the offset. So int key value long. So we insert, but where is our student? Now, insert binary search tree. Okay, let's ask for the student. We have the key value here. So yeah, let's, or we can do this in one step. We insert the student in the file. We will get our offset. So I don't need to ask it here. So it will be transparent. So we have only insert student, insert binary search tree, or insert student. Yeah. So I think in this way it's better. Okay. So each time we do what? We insert the student in the index, and in the same time we write the student into the file. So doing that, you get the offset. Now, what we want to be sure, and remember, this is a very important characteristic of a binary search tree. You will never allow duplicate keys. So the first thing that I want to be sure is that when I try to insert the student is not there. So I will write the student into the file only when I'm sure that this is a new student. Okay, so let's cover this these steps. So the first thing that we did was to check if we have a root. So if root equals null, it means this is a special case. You reach a dead end, or the initial binary search tree does not exist. So what do we do now? We create the student and we write that student into the file. Okay. Now insert student root. Where do we get our file name? We need it here. Const char file name. So this is like inserting the student into the file name and also into the index. Okay. So if the root node is null, it means we don't have it. So let's create one. Student index node, new node, equals create. That will create a key. You have init node. Okay, and we pass the student. Okay, so now we have created a new node and we initialize it. Now, what this node is missing is the offset. So at this point, we know for sure that this new student will be inserted into the index. So it means it's safe for us to write that into the file. So long offset equals write student into file. Which file? File name. Okay, which student? This one, student. And because now we have the offset, I can write new node offset equals offset. And that's it. Now we return new node. Okay, so in addition with what we have done last week, we need now to write the student into the file, get its offset, and set the offset of this new node. Because init node is just initializing the key, but it doesn't have the offset. Okay, so we need to set that after we write the student into the file. Perfect. So, and we return. Now, if we reach this place, it means that the root node exists. So we start traversing the tree in searching for a leaf node, or maybe we find the student. So it means it's already there. So we can decide to update it. Okay, and we know how to do that. Okay, so search for a possible location. So we do what? If, let's start once again with the pessimistic case. If root ID equals student ID, so let's say this is not search for a possible condition. This is actually check if the student is already here. So if this is the case, we don't do anything, or I think each time we choose to update it, right? So let's update the student, update the student values into the file, because we don't need to change here something in the binary search tree. In the binary search tree, you have only the offset and the key. That will not change. So let's update that. So update student from file, file name, student, new student value is student. It has the same ID. And now the offset, where do we get the offset? From here. We have it here. It's in the current node. So root offset, okay? Because we just found it. So here we update the student values into the file. And after that, let's say return null, okay? Or maybe you return the student. Sorry, we don't need to return null, is return root. So nothing has changed. This is, here we can do easily mistakes. So here we return the root, and you will understand why we need to return the root, because now we are searching for a possible location. So if root ID greater than student ID, we cover the equals. So if we are here, they are not equal. What do? Root. So if the current node ID is greater, it means we need to follow the left side because the new student ID is less than that. So root left equals insert, and this is the difference from the last week version. Here, each time we call insert, it will always be something current direction equals insert of that. And that's why you need to return root here, or new node. Because in this way, you initialize the left link of the current root. If it's nothing there, the next time you call insert student, you will reach a null pointer. You create a new node and you return its address. Who will get this address? This call here. And in this way, you initialize the left link of the current node with the new node address. Okay, so this is the characteristic of this approach, returning each time a node address. So insert student, which is the next root? Root left. What do we want to insert? Student into what file? File name. Okay, and else means only one thing. We already cover equals, but always check this one. Root right equals insert student into root right student and file name. Okay, and this is it. This is the other version of insert. Okay, so in this way we can insert in it's an alternative way to the last week implementation. So in this way you can easily insert into that binary search tree. Okay, so we know how to insert students here, and this insert will also write them into files here. So let's cover search. Okay, so we search for a key, and the search algorithm, which is exactly like the one from last week, will give us the student. But remember, the student is in the file, so we need to retrieve it from the file. The index will just help us get its offset. Okay, so in that way we will find it. Okay, so this is the search function, and the search function will give us a student. Okay, search. Now where do you want to search? In a binary or here we can receive the primary key. Okay, so primary key, and we need the ID, and this is the search key. Now this is, let's say this is the index in which we search, and this is the key value. Okay, and once again we need the file name. Now if you have a primary key which has a table name, you can easily use the table name for the file name. So in that way you don't need to ask each time the file name. Okay, so in that way you remove one argument from these functions. So now in this case let's keep the same approach, file name. Okay, so this will be our result, student result, init student. Just remind me to change init student to fix it here for null. So -1, empty name, empty faculty, null grades, and 0. So we need to update this one. Okay. Okay, so this is our result. Now, what we want to do is to search in a binary search tree. So once again, always start with the special cases. So let's say if index dot root ID equals key value. Yeah, because this is a recursive function, this will not work. We will always start from the beginning. So yeah, student index node root. Once again, we need the root. So it's a recursive version, so each time we need to pass a new root. If we pass the key, it will always start with the beginning because the key is always storing the root. So let's see if we found it. Yeah.
I didn't understand very well what the structure with the primary key was actually doing.
So the primary key is just a wrapper around this pointer. Now, if you don't like the primary key, it means that in order to handle the tree, you need only this tree root. Okay? Now, if you don't like seeing pointers, in this case, I created a structure which contains this pointer. You see, it's hiding the pointer from view, but it's still there. So it's just a wrapper. It's just a box in which I want to store the pointer because I don't want to see it. This is the only thing. Okay.
And the key name and table name?
And these are additional stuff, okay? Because otherwise, if you have only the pointer, then even I ask myself, why do you need an extra layer if you are just storing the pointer there? Don't you bring something new? So in this case, let's say I can add some extra details. So in this way, I want to simulate how a key is actually defined in a database. So you have multiple primary keys, and these are actually structures very similar to this one. And in this way, you have a collection of primary keys. So each time if you go through that collection of primary keys, you can know which is the column in that table, which is actually that primary key. Okay, so this is, let's say, a simulation of a primary key for a MySQL database. Okay, you need to store the column name, which is ID, name, whatever, and the table. Okay, and the database is actually storing a collection of primary keys. And in this way, the database can distinguish between them. So it knows for which table, for which column is this primary key. So that's why here, if I define an extra structure, in that case, I should bring something new, okay? Just to, let's say, justify this new structure. Because if you keep only the pointer, in that case, it's better to do it like this directly, okay? So this is the primary key. It's just a wrapper around the pointer itself. But like I said, it's optional. So you don't need it. You can play with the pointers directly. Okay, so here I need the root and not the primary key, because remember all these functions are recursive. So each time you need to call the same function again, but with a new node, either the left or the right of the current one. And if we write this search with the primary key here argument, I can't say, hey, now I'm here. Next time I'm calling you, move to the right side or the left side. So that's why I can't write search with a primary key value. I need the root, or let's say a pointer to a student node, student index node, because in this way, here, when I will continue to search recursively on the right or on the left side, I can call search again, and here I will pass root left or root right. That's why I realize I can't use the primary key here. So this is the corner case. We found it. Root ID equals key value. What do? Read the student data from the file. So how do we do that? Student fixed size student fixed student equals read student from file. Now, I think a read student from file was doing the conversion. So let's say result equals read student from file. Once again, let's see. File name, we have it, file name. Offset, it's here, it's in the current node. Remember, the binary search tree role now is to store the key and the associated offset. So root offset. Okay, so this will open the file, read the student, and return that to you. So we found it, return result. Okay, now, if they are not equal, we didn't cover the situation when this is empty. So this is another extra case. So if root equals null, okay, we reach a dead end. So return result, which is the default one here. Okay. If the root current node exists, but the ID is different, we need to continue searching. So here I will say if root ID greater than key value. Okay, which means the key value is less than current node. So we continue on the left side, return search root left key value file name. Okay, else return search on the opposite direction, root right key value and file name. And that's it. Okay, so this will go recursively. Each search will try to search on the left sibling or right sibling. You will continue going downwards into the tree. At some point, you may find the student. So here you return it, and each call here will get the result, return it to the upper layer until it's returned to the main call, to the initial call of search. Or you reach null, which means the key is not in your binary search tree. You return a dummy result because we have this contract here. We need to return a student every time. And you have the ID -1. So this is our way of checking if we found it or we didn't found it, that key value. Okay, now let's not forget to update init. So what I want to do is to check how init will behave if it's receiving 0 or null here. So here it's init student, and here where we copied the grades. So here, let's be sure that everything will be okay. So I'm back in init student. So let's say if grades equals null or number of grades equals 0, in that case, student grades equals null and student number of grades equals 0, else we do what we already have here. Okay, and in this way I remove the risk that malloc will crash here if we ask him to allocate 0 bytes. We can check the documentation of malloc, and maybe they are saying if you pass 0, nothing will happen. But in order to be sure, I do an extra check here. Okay, so let's test this very simple database. So we have an index, and each time we create the associated file. So let's test it. We have the primary key here, create key ID students. Let's insert some students here. So let's say insert student. This returns a student index node, okay, and it needs an index node. So this goes like here: ID key dot root equals insert student of ID key dot root. Okay, the student that I want to insert, let's say init student, let's pass a student here, ID, I don't know, 100, char name John, faculty CA, and grades null 0 grades. Okay, and file name students.bin or db. Yeah, let's make it db. Okay, now if we want to insert some students with some grades, let's define here some grades. So 999. Okay, int number of grades. So these are for testing, 3. So let's insert another one. I will copy this one here. So let's change the ID is 50. This is Alice. CA, and here I change grades and number of grades. Okay, and an extra one. This is Bob. Okay, let's say 150 grades number. Let's move Bob to marketing. Okay, so at this point, if we run this example, we should have printf \n the end. We should have what? We should have a file with a size that should be different than 0. Okay, now each time we run this example, the index is recreated. So here in a real application, you need to store the index also into a file. And when the application starts, you need to take the index from that file and rebuild it. Why? So if I run this application, you will have a file, students.db, which will have these 3 students with their offset. When you close the application, you lose the index. The file is still on the hard drive. And when you open it again and run the same section, you create a new index. You still have previous students in the students.db file, but you will always take into account in that session only the new ones. Okay, so in this case, this is a problem because we lose the index. So that's why in a real application, you need to store also the primary key when the application terminates into another file to store the binary search tree there into that file. And here, when the application starts, you need to load the index from that file. So in this way, the index will know about the previous students. Okay, so here the file will grow, but we will have each time only these students which we add in the last session. Okay, so let's say here we lose the index. The index should be written in a file in another file. Okay, so and here you need to restore it because otherwise you lose it. So you will rebuild it each time and you will know only about these ones. So let's test this. Run the application. Okay, yeah, I was expecting this one. Maybe you don't have it. It's already common stuff. So define, let's see, CRT secure, no warnings. Okay, let's try and give it another try. Build, rebuild. Okay, no compiler errors for me. Now, this was kind of dangerous. This is the first time I compile it. So yeah, this should not happen. You should do it as often as you can. Now let's run it. So let's run it in the debugger. Okay, I already have an exception, so we didn't went too far. So let's see where we are. We are here in insert student. And the exception thrown read access violation 0xCD. So here when we insert the student index node root, let's see. You see I'm here with root 0xCD, but I showed you also last week, we need to use the call stack. You see we are in the second call of insert student. Let's see what has happened in the previous one. So we were here. Root ID is 100 and we wanted to insert 50 and 100 is bigger than ID, and here we have root left because you see 0xCD. I think we forgot to initialize the left and right when we need the and we went on the left side, which was not okay. So let's see, insert root was okay, is not equal, and we do, and we are here from this line. Now let's check the root here. ID 0, 0. Why right and left are CD, CD? This is very similar with CCC. So let's stop and let's add a breakpoint here after the first insert. F5. Now we are here. Root is null. Right, left. Yeah, because it's null, it doesn't matter. So let's dive into the function. And this means let's use debug step into, which is F11. So F11, we are here in init student. So this is initializing the student, no problem here. F10, this is this init student here. Again, F11, I need to see what's happening here in the first insert. Now we are here. Now the root is null. We dive into this path. Student index node equals new node. Let's see, new node. You see it? Right, left, CD, CD, CD. So let's see init node. Okay, init node is around here. Init node. Yeah, classic error. We forgot to initialize left and right. Okay, like I said, this is classic. Happens to everybody. Okay, new node, right, null. And I think I even disregard what I'm saying to you each seminar to, yeah, this is the problem with malloc. This is not new. New behaves differently in C++. So here you see when it's creating the new node, it's not using these values here. New, it's, I think, yeah, because it's calling the constructor. So yeah, so as a conclusion, every time you init a node, set your pointers to null or other values. Okay, let's try again. So F5. Okay, everything was okay. So let me prove that to you. Control F5. Okay, exit code 0. Now let's check the file size. Remember, each time we run the application, the file size will increase because it will just add this new stuff. So right click on Seminar 11, open folder in File Explorer. Let me show you that. So you have what? Students DB, properties. You see it has size.
I'm sorry, how did you get?
How did I get here?
Yes.
Right click here, open folder in File Explorer. You see
Okay,
it?
thank you. Yeah.
So this is the fastest way to find where your sources are. And generally the files are right near the CPP files. So it will get you there. Okay, so let's check the size. You see, it's quite big because we run it, I think in my case, I run it 2 or 3 times. So it has already almost 12 kilobytes. Okay, so each time it will increase with the new sizes. Now, let's see if this works. Okay, so new share. How do I know this will work? So here we are inserting students. Let's search for them. So student, student equals search student. Now, what do we pass? We pass the primary key, id key dot root. The key value, let's search for Alice. Let's see Alice data, and the file name, once again, studentsdb. Okay, so let's print it. Print student. Let's see if we see Alice data. So Control F5 again. Where is my console? Here it is. Okay, I see nothing, grades, the end. Yeah, so it's not working. Let's see what search is doing. Once again, I will add here a breakpoint. F5. So we stop here. F11, I want to dive into search. So F11, root is 150. Oops, there is an issue here. The primary key is not initialized. So something is happening here with insert student. Let's add a breakpoint here. So F5. Now, initially the root is null. After the first insert, the root is now, yeah, it has IDs 100. Yeah, that's great. I was thinking at last week, I was expecting to see the student, but the student is not there. We have only its ID. So after the second insert, the root is now 50, which is not okay because we lose the previous root. So F10 again, root is now 150, and you see null, null. So we have another issue in insert. Now in Visual Studio, if you want to check a function, you don't need to scroll it, and we quite have a significant number of lines of code. So if you want to jump to the function definition, just hit Control. So if you keep Control pressed, now these names becomes hyperlinks or similar with hyperlinks. And if you now click on the function name, so I'm pressing Control, okay, and if I now click init student, I will be redirected here, okay, because otherwise you have seen earlier you need to scroll up and downwards. This is not productive. So let's see why here we don't change, sorry, not init student, my mistake, it was insert student. Okay, so if root null, return new node. But if root ID equals return root, searching for a possible location, this is the problem, and this is the problem with recursion. You see, each time we need to return something. So if you reach a dead end, you return the new node. Now, this will return to left, and this will return to right. But here, what will happen? Return root. Why these links are not initialized? Left, right, left, right. Student node root. So we have root. Why they are not return new node? Yeah, let's put a breakpoint here. I'm missing something. I will remove the other breakpoints. So I want to reach here, insert student. So F5 again. Now root is null. So let's see what is happening. F10, we just created a new one. ID 100, left and right are null. Okay, so F5 again. This is the second insert. Here we want to insert with student with ID 50, and why the root is null? We receive a null, so ID root should take insert student. Okay, let's see what we return from insert. Stop the debugger. Why the root is not changing? So return new node. So let's see, F5 again. F10, new node is created. We return it. So now we are here. Root is null, and this should get the new node. Okay, it gets that 100, and now the root is 100. Okay, so F11, we go to init. I don't care about this one. Okay, root is still 100, and here we need to pass the same value. So F11, we are here, is 100. Great. If root is not null, is 100. Okay. Root ID is 100. We need to insert 50. Great. So we don't go by that path. Root ID is greater than student ID. So we go here, and left is null. Okay. F11 again, once again, we are in insert student. The root now is null. We create a new node for student 50. Okay, new node is 50. We return this to the previous recursive call, and now left should be pointing to 50. And okay, yeah, I don't want to have mistaken. And now we return nothing. So root is expecting something from insert node. So here for insert, please add this part, return root. Okay, so if we search for on left or right, when we come back, we need to return the root again, because otherwise we lose it. Okay, it's like, I think here for different compilers will give you a runtime exception that you don't return on all paths. In Java, you'll get this compiler error, but not for this one. So you see here, we have two paths in the execution of insert student, which are returning nothing. Okay, so let's see if this works now. Control F5. No.
But wasn't it? Oh, okay.
Yeah, I still get, yeah, let's put a breakpoint. I still get an empty data student. So let's see, root now is 100. On the right, you have ID 150, and left, you have 50. But the offset is 0. Okay, you see, this is the problem. We don't save the offset. So for all our nodes, the offset is 0. Okay, so once again, insert has an issue here. We don't get this offset. So write student into file. Let's see what's happening here. So I'll put here a breakpoint. So F5, we are into write student. This should return the offset. You get the file name, and here we want to insert student 100. So F10, let's see, open the file. File has the pointer PF. It's different than null, so it's okay. Get the current offset. So let's see what's the current offset. Okay, ftel. I think it's not ftel, is ftelg. Let me check ftel. What ftel is doing? So the CRK returns the current file position of the given stream. Okay, returns the current of a given stream. Okay, the function return okay of the position if okay one on the global value is set to a positive value. So yeah,
Don't we have to be with the cursor of the file to the end?
yes,
No.
we are at the end. We open the file in append mode, right? So if you remember, when we open the file here, this is append plus binary. Okay, yeah, let's see where append plus binary. Yeah, let's check the append plus binary option in C. What this is doing. Yeah, someone is saying append plus binary plus. I search it on Google, and yeah, let's try with this append binary plus. Okay, I still have the same breakpoint. Let's see, F10. No, it's still 0. The file is there. I think it already, in my case, reached 50 kilobytes. So why we are not there? Let's search again for open C file in append mode. Okay. Okay, append for writing. Okay, the similar at the end of the file. Right of the file. Okay, okay, or similar. Okay. So why allow me opening the file. Let's see. Append to another file. C. Append and read from a file. Because we want to do the same operations in the same. Reading and appending to the same file. Yes, see. A plus. Okay, okay, A plus. The problem is that you're reading and writing from the same file. Your reads and writes interact. Yes, I know that. Opening the file with no mode A plus says the file position at the beginning. It's not deleting the. Yeah, but it's not deleting. Read binary plus. It's not doing trunc. We can check with that. Okay, no. Okay, so we can check with that binary, but so opening the file with mode, okay, so it's okay. So the first F gets reads the first line, but in append mode, all writes are performed at the end of the file. Ah, okay. So reading, so the first is the file to the end of the file, then writes, since there is a single file position for both reading and writing, the next call is performed at the end of the file. Okay, so this is the problem with a binary plus here. So when you open the file, you are at the end of the file, but somehow we jump at the beginning. Okay, now someone is saying read binary is not truncating the file. Okay, so let's try with this part. So F5, write student into file. Let's see, F10, we open the file, F10. We still need to move to the end of the file. Okay, so let's do that manually. We still, okay, we're on append mode. Okay. So we open the file for reading and writing. So every time we write, we move ourselves at the end, and for reading, okay, so yeah, let's go for this approach. So what changes we need to do? When we open the file for writing here, we open now the file with write binary plus. Okay, so get the current offset. It means at the end. So get the offset at the end of the file. So in order to do that, we do this. fseek, fseek into file. Sorry, I pressed insert. File.pf. Where is the offset where I want to go? 0, which is the origin. It's seek end. So in this way, we position ourselves at the end of the file, and now we should get the offset there. And this is for writing. Now for updating, here we don't need to do that. Yeah, we need it because here we check get the current offset in order to validate this offset. So once again, we need to do this. Okay, so here is like we position the cursor at the end of the file because we need each time to check the offset. So I added this line here, fseek file pf0 seek end in write student file, and the same line goes here into update student from file, because here we need to do the same here. Yeah, and the story goes on. Okay, the file does not
Let's just stick with A plus B when we open the file.
Okay, so yeah, but we still need to do this fseek file pf. Yeah, that's why it's not truncating. I was thinking at write binary plus wb plus, that is truncating the file. Read bw will open it only for reading, so it's not safe. Okay, yeah, let's stick with a plus binary. but I think we still need fseek here. So in update fseek again, file pf0 seekend, and also in read student from file, because we need to do the same check. Once again, I need the same line here. And after that, we position ourselves to the given offset. So open file, let's change it back to read plus binary, or it was append, sorry, append plus binary. Now let's see if we now get the current offset, if that fseek helps. F5, okay, fseek, yay, now we have it. Okay, so I think this will solve all our issues. So just add fseek file pf0 seekend in write, and also read and update before this line. Okay. Okay, now let's continue. Remove the breakpoint. F5. Let's remove this breakpoint also. F5. Okay, and I see Alice. Let me show you Alice. Control F5. Okay, so now we found Alice. We search for it by its index. Let's let's change and let's search for another one. Let's search for Bob 50. Let's see Bob. Control F5. Okay, marketing 9999. Okay, and now let's search for something that does not exist in the index. For example, I want to search for 34. Control F5. Okay, and it's saying to us that thing doesn't exist. Okay, so it's returning nothing. No name, no faculty. If we print the ID, we didn't print it. You can do that change. You will see that the ID is -1. And if I want to convince you about that, we can do the check here. So if student ID different than -1, print it. Otherwise, print another message. Else, printf no value for key, let's say 34 in this case. Yeah, I can write it here. Okay, so Control F5, and that will return -1. Just a moment. Control F5 again. Yeah. So new share, and you have it here. No value for key 34. Okay. So this is the, let's say, a quite complex example, which is covering a real index that it's actually storing the offset of your data into the file. And in this way, we covered files. Now, for an open subject, if I would be the person to create the subjects, but it's not the case. I'm limiting only to managing this only seminar. Now, for data structures and for any open subject, not having file is like not using the entire spectrum of what data structures can offer to you. So files, I think it's something you will get for sure, either text files or binary files. And now the only thing that is, let's say, unknown is which data structure you need to implement. So if I would be in your place, I will prepare files. Okay, because like I said, without a file, you store the data into RAM, but this is never going to happen. Okay, you lose the data. Okay, but with files, it's let's say it's more practical, and you are getting close to a real example. Okay, so with this, we also cover writing and reading binary files.